Hi everybody, this video goes over section 4 of chapter 7, and here we are going to present the double angle and half angle identities, among others. Specifically, we're going to present the double angle identities, followed by the product to sum and the sum to product identities, the half angle identities. Then we're going to talk about how to verify various trigonomic identities using these as tools, and we have an application to go through. These are the double angle identities. Now, in the interest of time, we are not going to derive them. However, they can be derived from the identities that we have learned earlier, and our purpose is to learn how to use these identities, which will be the focus of this particular video. And with that in mind, here is our first example. Here we are given the sine of theta, which happens to be equal to 3/5. And we're told that the cosine of theta is negative, which means that we are probably in quadrant 2. And we want to find the value for cosine of 2 theta, sine of 2 theta, and tangent of 2 theta. Okay, so let's go ahead and do that. Now notice that the identity for sine of 2 theta is 2 times sine of theta times cosine of theta. Okay, well, we don't know what cosine of theta is yet, so we need to figure that out. And of course, we can figure that out using the Pythagorean identity, and rearranging that a little bit, we will have that the cosine squared of theta is equal to 1 minus sine squared theta. And evaluating that for the case where sine is equal to 3/5, we can have, well, instead of 1, how about 25 over 25 minus sine squared theta squared, which will be 3 squared, which is 9, divided by 5 squared, which is 25. And if we simplify that, we are going to have that cosine squared theta is equal to 16 over 25. Therefore, cosine of theta is going to be, since it's negative, the negative square root of 16 over 25, or negative 4/5. So we have sine of theta is 3/5. We have that the cosine of theta is equal to negative 4/5. And now we have everything we need to solve this problem and actually all the other problems. Okay, so sine of 2 theta is going to be equal to 2 times the sine of theta, which is 3/5, times the cosine of theta, which is negative 4/5. Negative 4/5. Almost forgot the negative sign there. And that will be equal to, well, 2 times 3 is 6, times negative 4 is negative 24 over 25. And there we go. Now to find the cosine of 2 theta, we actually have a number of identities we can use, but since we know what cosine squared theta is and what sine squared theta is, why don't we just go ahead and use that one. So we will have that cosine of 2 theta is equal to cosine squared theta minus sine squared theta. Well, cosine squared theta is 16 over 25. We've already figured that out. Minus, and sine squared theta is going to be 9/25. And 16 minus 9 is 7. And we'll have 25 down here. So here we have the cosine of 2 theta is 7/25. Now for tangent 2 theta, we can go ahead and we can use the identity that this is equal to 2 tangent of theta divided by 1 minus tangent squared of theta. But we really don't have to, do we? Because tangent of 2 theta, using the quotient identity, is equal to sine of 2 theta divided by cosine of 2 theta, which we have already computed. Sine of 2 theta is negative 24 over 25. Cosine of 2 theta is 7 over 25. Therefore, tangent of 2 theta is negative 24 over 7. So even though you have that identity at your disposal, since we already know what sine and cosine are, what sine 2 theta and cosine 2 theta are, it's a lot easier just to use this root. Here's example 2. And you might say to yourself, what does this example have to do with double angle identities? Well, just recall that the sine of 2a is equal to 2 times the sine of a times the cosine of a. Well, if that's the case, then the product of sine a and cosine a is going to be equal to 1/2 the sine of the double angle, 2a. Well, here we have the product of sine of 165 degrees and cosine 165 degrees, and this will be equal to 1/2 times the sine of twice this, which would be the sine of 330 degrees. Now, if you recall, 330 degrees is in quadrant 4. Furthermore, it has a reference angle of 30 degrees. And the sine of 30 degrees is equal to 1/2. Okay? And since we're in quadrant 4, all the sine values are going to be negative. So this is going to be equal to 1/2 times the sine of 330, which is basically the sine of 30 negated. So this is going to be equal to negative 1/2, which will give you your final result of negative 1/4. And then next, what you're going to find, at least in your homework, is the opportunity to use the identities that we presented thus far to actually write a multi-angle identity. And here we want to write an identity that expresses cosine of 3 times x in terms of cosine of x. And how in the world could we do this? Well, we've dealt with double identities, so maybe we want to write this as, we want to write cosine 3x as the cosine of 2x plus x. If we do, then we can apply the sum and difference identities that we actually learned in our last video to this, and then we will have that this is equal to cosine of 2x times cosine of x minus sine of 2x times sine of x. And now we have double angle identities. For example, we can use our first double angle identity for this and rewrite this as cosine squared x minus sine squared x. And of course, all of this will be multiplied by cosine of x. And here we can use the identity, the double angle identity for sine, which will give us 2 sine of x cosine of x, which of course will be multiplied by sine of x. Okay, it looks a little messy, but maybe we can clean this sucker up. So let's use our distributive property here, and we will have cosine squared x times cosine of x, which will be cosine cubed x, minus sine squared times cosine, that will be sine squared x times cosine squared x. No, cosine of x, not squared. Now here we have two sines, they can square, and we will have minus 2 sine squared x cosine of x. Okay, well here we have like terms. We have sine squared and cosine, so these can be combined, and that will give us cosine cubed x minus 3 times sine squared x cosine of x. Well, we still have that sine term here that we need to deal with. However, we do have our trigonomic identity. We can actually write this. We can actually write that as 1 minus cosine squared x. So let's go ahead and do that. And if we do, we will have cosine cubed x minus 3 times the quantity 1 minus cosine squared x, all this times cosine of x. Well, we need to distribute again. Let's go ahead and do that. Actually, we need to distribute two ways, but we can actually do both at once. And if we do, we will have cosine of 3x, or cosine cubed x, minus 3 times cosine of x, and then minus 3 times minus cosine of x will give us, or minus 3 times minus cosine squared of x will give us positive 3 cosine squared, times cosine will give us a cosine cubed, so all this will give us plus 3 cosine cubed x. And now it's looking a little better. Here we have like terms. I have a cosine cubed here, a cosine cubed there. They can be combined, and we will have 4 cosine cubed x minus 3 cosine of x. Now, is this written in terms of cosine of x? Well, yes, it is, because this is basically cosine of x multiplied by itself 3 times, and this actually is indeed the identity that we're looking for. Okay, so that was fun. And this brings us to the product to sum identities. So it turns out that if you have the product of two cosines, you can write them as 1/2 of the cosine of the sum of the angles plus the cosine of the difference of the angles. Similarly, you can come up with similar expressions for sine and sine for the product of two sines, or for the product of sine and cosine, or for the product of cosine and sine. These can really be easily derived from the sum and difference identities that we actually used before, and you can sort of envision how you can do that, but that is not the purpose of this course or this particular section. Once again, our purpose is primarily how to use them. And let's do that in this particular example. Here we have the product. We have 6 times sine of 40 degrees times sine of 15 degrees, and we want to write this as the sum or difference of two functions. So to do this, we want to use this particular identity. So we are going to write this as 6 times 1/2 the cosine of the difference of the two angles, which will be 40 minus 15, minus cosine the sum of the two angles, which will be 40 plus 15. We can do some simplification here. First one is a 6 times 1/2. Well, that's just simply 3. Okay. 40 minus 15, that's cosine of 25. Cosine of 25 degrees. 40 plus 15, well, that's cosine of 55 degrees. And then distributing, you will have our desired result, which will be 3 cosine 25 minus 3 cosine 55. And that's pretty much as far as we want to go. Now, since we've talked about product to sum identities, yes, you've guessed it, we have sum to product identities, which are pretty much derived the exact same way. Actually, what you can do is you can start here, do a change of variables, and that will arrive you at this particular problem, or at this set of identities. The only real sticker is, just notice that when you are subtracting cosines, you have a -2 here that you need to contend with. And of course, once again, we're not interested in deriving these, although it is interesting and useful. However, we do want to use them, and let's do that here. Here we want to write the cosine of 3 theta plus the cosine of 7 theta as the product of two functions. Well, before we do that, let's compute 3 theta plus 7 theta over 2 and 3 theta minus 7 theta divided by 2. And if we do over here, we have 5 theta, 10 theta divided by 2, which is 5 theta. Here we're going to have negative 4 theta over 2, which is negative 2 theta. So that gives us this gives our a plus b over 2 and our a minus b over 2. And then we need to decide which identity we want to use. And chances are, since we are adding two cosines, this is the identity that we want to use. Okay. So we are going to have that the cosine of 3 theta plus the cosine of 7 theta is going to be equal to 2 times the cosine of this value, which is 5 theta, times the cosine of this value, which is negative 2 theta. And now notice here that cosine is an even function, so we can simplify this a little bit, because cosine of negative 2 theta is going to be equal to cosine of 2 theta, so we can write this as 2 cosine 5 theta times cosine 2 theta. And all we're doing, once again, is using the identity that this is equal to 2 times the cosine of 3 theta plus 7 theta over 2 times the cosine of 3 theta minus 7 theta over 2. That's pretty much all that we're doing here. Once again, using this identity right here. Okay, and this brings us to the half angle identities. And these do look somewhat taunting because we have square roots, we have plus or minuses. But the big thing to indicate here is that first thing is that the plus or minus terms basically indicate the sign that you want to choose first based upon your function, and also the quadrant where this particular angle lies. For example, if a over 2 is in quadrant 3, or quadrant 1 or 3, we take the positive square root. If a over 2 is in quadrant 1 or 2, we take the negative square root. And that also applies for cosine and sine depending upon what quadrant they're in. So let's see how these things work in an example. So here we want to find the exact value of sine of 22.5 using the half angle identity. And that means that we want to use this half angle identity right here. So we're going to have that the wrong way. We're going to have that the sine of 22.5 is going to be equal to, well, remember this is a quadrant 1, so we're going to take the positive square root of 1 minus cosine twice that value, which conveniently is 45 degrees, divided by 2. Evaluating the cosine of 45 degrees, we are going to have 1 minus the square root of 2 over 2, all over 2. And of course, we're going to take the square root of all this, the positive square root. Now we need to deal with this fraction. We can do this by multiplying this term by 1, or more specifically, 2 over 2. And if we do, we will have, well, 2 times 1 is 2. This 2 in the numerator cancels out that 2, so we're left with negative root 2 divided by 4. And of course, we're taking the positive square root of all of this. Well, 4 is a perfect square. That's going to be equal to 2. So we have 2 in the denominator, and then we are left with 2 minus the square root of 2. And that, believe it or not, is our answer. We do not want to take it any further than that. Now in this example, we are given the value for cosine of s. It's equal to negative 3 sevenths. And we're told that s lies in between pi and 3 pi over 2, which essentially is quadrant 3. Okay, and we want to find sine of s over 2 and cosine of s over 2. Now before we do that, we need to figure out the quadrant in which s over 2 lies in. So we can do that by dividing this entire thing by 2. Divided by 2 here, divide by 2 here, and of course divide by 2 here. And if we do, we will have that s over 2 is going to be greater than pi over 2, but less than 3 pi over 4. And that means that s over 2 is going to be in quadrant 2. Okay, well, if 1/2 s is in quadrant 2, that means that sine of 1/2 s is going to be positive, and cosine of s over 2 is going to be negative. So we need to keep that in mind when we have to compute our square roots. Okay, so to find sine of s over 2, that we've actually used that half angle identity before. That's going to be equal to, well, the positive square root of 1 minus cosine of s divided by 2. All right, well, we can do that. Cosine of s is negative 3/7, so this is going to be the positive square root of, well, let me write this as 7 over 7 minus negative 3 over 7 is going to be plus 3 over 7, all divided by 2, taking the square root. That is going to be 10 over 7 divided by 2, once again taking the square root, and then that is going to give us 10 over 14, once again taking the square root. Now notice here that 10 and 14 have a common factor of 2, so we can actually simplify that fraction, and that will give us the square root of 5/7. Now notice that we have a radical in the denominator. We need to rationalize that. We can do that by multiplying this by 1, or more specifically the square root of 7 over the square root of 7. And if we do, we will have the square root of 5 times 7, which is the square root of 35, divided by 7, and that is our answer. Whew. Okay, what about cosine of s over 2? Well, the half angle identity for cosine of s over 2 is the square root of 1 plus cosine of s all over 2. But since we're in quadrant 2 and cosine of s over 2 is going to be negative, we need to take the negative square root. So that's what we're going to do here. Okay, working through this, we can write 1 as 7 over 7, and then the cosine of s is negative 3/7, so it's going to be minus 3/7. All that over 2. We're taking the negative square root. That is going to be equal to 4 over 7 divided by 2, negative square root. That will be equal to the negative square root of 4 over 14, which simplifies to the negative square root of 2/7. Okay, we need to rationalize the denominator. We can do that by multiplying this by 1, or more specifically the square root of 7 divided by the square root of 7. If we do, then we have our result of cosine of s over 2 being equal to negative the square root of 2 times 7, which is 14. And then in the denominator, we will just simply have 7. And there we go. That's pretty much how we do that. Now, one of the things that you're going to be asked to do in this particular homework is verify a collection of identities. And in your homework, they don't just give you the problem and tell you to verify it, they actually walk you through it, so that will be helpful. Here, we're going to go ahead and do this one, and I will, of course, walk you through that. And typically, the approach that you want to use when you are verifying an identity is to first look at the more complicated side, which would be right here. So let's go ahead and do that. So what can we do with all of this? Well, one of the things that we can do is we can actually express secant in terms of cosine. That might help us a little bit. So let's go ahead and do that. So we can write this as 1 over cosine of theta plus cosine of theta minus 2 over 1 over cosine of theta minus cosine of theta. You're asking, well, how the heck does that help? Not sure, but notice that we can actually get rid of this fraction here by multiplying this by multiplying this entire expression by cosine of theta divided by cosine of theta. And if I do, I will have, well, that's canceled, so that'll be 1. Here I will have cosine squared theta minus 2 cosine theta. In the denominator, I will have 1, cosine times 1 over cosine, that's 1, minus cosine squared theta. Well, that's interesting. It turns out that using the Pythagorean identity, that actually is sine squared theta. So now I have in the numerator sine squared theta. What do I have up here? Well, I can rearrange this to 1 minus 2 cosine theta plus cosine squared theta. And this is a perfect square. I can write this as 1 minus cosine of theta, the entire thing squared, and that will be over sine squared theta. Or this is 1 minus cosine theta divided by sine of theta, the entire thing squared. Now let's go back to our half angle identity. This is our half angle identity for tangent of theta. We have this squared. So as a consequence, this is equal to tangent squared theta over 2. And we have just verified the identity. Our last problem is to do an application. So here we are talking about an appliance, any appliance that's plugged into a typical European outlet. And the point of the matter is that since it's an AC signal, the power consumed is not constant. It varies with the frequency of the signal, which of course is a high frequency. And it turns out that in Europe, their AC signal varies at 50 cycles per second. Ours varies at 60 cycles per second. As a consequence, their power usage as a function of time follows this particular model. Now, power is always equal to V squared over R, where R is the input resistance or the load resistance for the appliance at hand, and then again, and once again, this is basically nothing more than V squared. What we need to do is use this particular identity to determine the values of A, C, and omega so that it fits this particular model. Okay, so that's what we're going to do. The first thing that we're going to need to do is to rearrange this identity, and if we do, so that is in terms of sine squared theta, and if we do, we will have that sine squared theta is equal to 1/2 minus 1/2 cosine 2 theta. And then what we want to do is we want to substitute this value into sine squared theta. And if we do, we will have that W of t is equal to 311 over 686 times 1/2 minus 1/2 cosine of 200 pi times t. Okay, doing a little rearranging, we can write this as negative 311 over 686 times 2, which is 1372, times cosine of 200 pi t plus 311 divided by 1372. Okay, and that pretty much answers the question. It'll be for A, we will have that A is equal to negative 311 over 1372. We will have that C is positive 311 over 1372. And then we will have that omega is equal to 200 pi. And that answers the question. And that is all I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.